So let's start by taking ourselves back to the magical land of the early 2000s. We are at Google. At this time, I was in junior high school, I think. And so Google has this thing that they have to do all the time, and that is for literally every page on the internet, they have to do something like this, which is build an inverted index. So you want to know for the word cow, if someone's going to type that into a search box, every single website on the internet that has the word cow in it. So as you know, there are a lot of websites. There were fewer websites at the time, but still quite a few. And in addition to this, they had tons of general data preparation and analysis tasks that ran over enormous amounts of data. Here we go. So it's hard to do that on a single computer. Even really powerful, fast supercomputers, it's hard to do it on, and they are very, very expensive. So the basic idea that they came up with was you get a cluster of tens, hundreds, thousands, 10,000s of commodity machines, and you get them all to work together on solving these types of problems. So that is all nice and dandy, but if I want to be doing like basic web analytics, if I want to be building a search engine, I don't want to have to think about all the, oops, yeah, I'm using the wrong computer, thank you. I don't want to have to be thinking about all the complications that arise when you're trying to build distributed systems. You know, anything can fail at any time, so you have to maintain some sort of consistency. It gets very complicated and very unhappy very quickly. So these people at Google came up with this idea, and this idea was MapReduce. So how does MapReduce work? At a very high level, you as a MapReduce programmer write your program in terms of two functions, map function and a reduce function. And the framework pretty much takes care of the rest. So what are these functions? Well, let's get that a little bit later. So what are these functions like? What a map function does is it takes as input some key value pair, and then it just outputs some other key value pair. The reduce function, so in between map and reduce, this magic happens where, we don't have a whiteboard, do we? No, it's too small. This magic happens where all the keys that were outputted from the map function, all the values corresponding to them get combined, sorted together, and sent to a reducer. So I'm going to go into this a little more heavily in the next slide. And so a reducer also gets a key with a list of values that correspond to it as input, and outputs something else. So let's look at sort of the canonical MapReduce function, or the canonical MapReduce program is word count. So here we are back as Google, or really anyone, and we have some enormous corpus of tons and tons of documents, and we want to do some sort of frequency analysis on it. So for every word that shows up in those documents, what we would like to be able to do is output a count of how many times that word appears in all the documents. So we start with our map function. And our map function is very simple. Each input to the map function is one of the documents in our corpus. And an output is, so we take that document, we read it, we parse out, tokenize all the words. And then for each word in that document, we are able to output that word mapped to the value 1. Does that make sense? We're saying there's one of that word in that document. Okay, so at the end of all our mapping, we've called this map function on every document in our corpus, and we have tons and tons of these output key value pairs, right? For every single word in every document that we have that mapped to the letter 1. So this magic happens in between map and reduce, where for all the keys, for all the output keys of our map function, the ones that are the same are grouped together. So the word cow, cow is mapped to 1, let's say maybe 100,000 times in our corpus. So we go to all those things, and a single reducer gets cow as a key and then 100,000 ones as the value. So the job of the reducer then is to just sum all those ones and output that. So the reducer is going to output cow and then 100,000. Any questions there? Okay. Back to here's our Java main function. We want to run this word count program that we just wrote. And so this is some simple Hadoop code to do just that thing. We create a job configuration object which represents this MapReduce job that we want to run. We tell it, so our outputs are going to be words mapped to numbers. So we tell it, if you can't read it, it's set output key class to text.class. That's Hadoop's way of saying string. And set output value class to int writable, which is Hadoop's way of saying integer that is easy for it to serialize, to send like across the network and stuff like that. Then we give it our mapper class and our reducer class. Those are the classes that we defined back here. We have this set input format and set output format business. That's something we'll get to later. In general, MapReduce jobs are reading and writing to this distributed file system called Hdfs. And the input and output formats tell us what formats the files will be in on Hdfs. Will they be text files? Will they be binary files? Do they have any like special structure that we have to know about? Last of all, the paths of the files, and then we can run our job and send it off to a cluster of machines to get it working. 1 second. Okay, so let's talk about Hadoop in general a little more. So where does all this data come from, and where does it go? Hadoop is the core components of Hadoop are these two things, Hdfs and MapReduce. This is actually changing recently with Yarn, so if anyone's curious about that, I can tell you about that. But this is what you need to know for now. So Hdfs, the Hadoop distributed file system, is this file system that runs on a cluster and stores all of its data across different nodes, across different commodity machines. It replicates data, so you expect that your machines might die on you, and luckily there will be your data on other machines, and it'll heal itself and replicate that again. And so you use the same machines for Hdfs and MapReduce so that the computation that you're doing on your data is in the exact same place as your data. And what's great about Hdfs is it scales linearly with the number of machines. So if you have like a 4,000 node cluster, you can scale to hundreds of petabytes, which is a lot of bytes. Any questions about Hadoop, Hdfs? Okay. So here's how MapReduce works under the covers. So sort of a high-level diagram. In terms of how the system works itself, there's this master process called the job tracker. And the job tracker is what you tell to run jobs for you. It's in charge of pretty much everything that goes on. It is a single point of failure, so if it dies, you will have to manually restart it to get your MapReduce jobs working again. And that'll run on one machine in your cluster. And on all the other machines, you run these processes called task trackers. And a task tracker's job is basically to hear from the job tracker that there's some maps or reducers that it needs to run, and then run those. So on everything that we're seeing in this diagram, let's imagine that each of those little boxes is a different computer. There's a task tracker running on that computer that is running these processes. So when we get our enormous corpus as input, and let's imagine for the sake of simplicity that it's one huge file, and each line in that file is a document. MapReduce and Hadoop will for us, it will split up this file into different partitions. So if we have 100,000 lines and 20 mappers, it'll send however many lines per mapper that is, to each one. It reads all those inputs and sends the relevant data to each mapper. For each line, the map function that we talked about earlier, like that word count, is called on that line. And that map function produces some number of output key values, and those were the words mapped to the ones that we talked about. So then we have the magic that I have been alluding to, which is the shuffle phase. So the maps are all done. The job tracker tells the task trackers to start a bunch of reducers on other machines. And in addition to starting them, it tells them, okay, so these are the mappers that run, and they have data that you might want. So a reducer, let's say that top reducer is in charge of all the keys from cow to milk. So that reducer will go out to every mapper that outputted a cow key and ask it whether it has ask it for all its cow to one key value mappings. So they all get, from multiple mappers, they all get sent over to that reducer. And the reducer is then able to merge those together, merge cow, comma 1, cow, comma 1 on that machine with cow, comma 1 on another machine. Then it supplies the reduce function that we've defined with cow mapped to like 1 1,000 times, or if we did it your better way, cow mapped to 1 or 5 or whatever it is. The reduce function runs, and then Hadoop will take care of writing the output of that back to Hdfs wherever you tell it to. Let's see. Okay, so the last thing that we didn't cover is the real reason we need MapReduce in the first place, and this is more under the cover stuff. What happens if a task fails while you're trying to run your program? Like one of your mappers dies. So in a naive implementation, your whole job would be destroyed, and you would need to just start over again. But what MapReduce does nicely for you is it will rerun that task for you. So you don't have to recompute all the data, just whatever amount of data was assigned to that particular task needs to be redone. Okay, so are there any questions about that? I'm going to go into one more example. Okay, cool. So another canonical MapReduce example is a program to calculate pi. So if you ever heard of the Monte Carlo method of calculating pi, basically what you do is you imagine you have this, I know this is more of a rectangle, but you imagine you have this square and a circle inside of it, and you have millions and millions of darts. And you keep throwing darts at that dartboard so they'll land uniformly somewhere in the square. Doing that, you can get a sense for the area of that circle as it pertains to the square surrounding it. So you'll have, let's say, out of your 10,000 darts, I'm not sure what pi divided by 4 is, but you'll have some proportion of them that land inside the circle. I mean, it's very easy to calculate when you pick two random numbers if that is close to the center of a circle or not. and you'll have some that lie outside the circle. So using the basic formula, area equals pi r squared, you can look at the ratio between the area of the square and the area of the circle and get a pretty good estimate for pi. So how would we do this? How would we make this better in MapReduce? Would anybody be interested in taking a guess of what that MapReduce program would look like? Okay, I'll put no one on the spot. Cool. So in this case, the way we're doing it, this is functionally equivalent to the way you explained it. Yours might actually be even better. But we're going to predefine for each mapper the number of darts it's going to throw at that board. And then let's say we have like 2,000 mappers, and we want to define the number of darts as 100. We send we configure 100 as this num to run configuration parameter, and that'll get sent over to our MapReduce jobs. So the mapper looks, again, pretty simple. What we do is for the number of darts that we want to throw, we pick a random number. We figure out whether it is inside the circle. And if it is, we increment this num inside. In this case, each mapper only outputs a single key value pair, and that's because there's no reason to do more. There's no reason to do one for each dart. We can just sum all of them to give to the reducer. Whoa, this is I'm really terrible at this. Yeah, we're back here. This is again. So we just want to go down. Yeah. Scroll. Oh, I see. We touched that. Okay, that's out of the screen. Where'd it go though? Oh, okay, wrong slide. Okay, so here is our reducer. And for this pi Monte Carlo simulation, we only have one reducer. So every mapper, to achieve this, every mapper outputs the same key, but there may be different values for the different number of darts that hit inside. So the reducer then gets all the different values, the number of darts that landed inside the circle from the mapper. It sums all of those and divides by the total number of darts that were thrown. And then it can easily estimate pi as 4 times that ratio. Let's see. And then it sends a single output, which is its estimate for pi, out to be written to Hdfs. Does anybody have any questions about that? So this is more of a best practice than how MapReduce works. This is the distributed cache. So it's very common that in addition to whatever MapReduce computation that you want to be doing, you'll have some auxiliary files that need to be used. Like, for example, if you are actually doing an inverted internet index of the internet, you'd probably want a list of basic words like and, the, that you aren't actually going to include in your index. This is used for joins, which we can talk about later. So MapReduce allows you in your job setup code to add these files as a cache to the cache, and then the framework will. Here, I'm going to zoom in. Will take care of distributing those files to computers that your mappers are on, so they're able to use them when you need them. This is also how it sends out your mapper jar to all the files, and you can send additional jars that you might need to use. Any questions about that? Cool. So what's so great about MapReduce? What's so great is that it scales linearly with either the size of the data or the complexity of your analysis if you use the right algorithms. So it's great for both doing data parallel type algorithms like the word count that we talked about, where you have tons and tons of data. Let's say you have logs for your website, terabytes and terabytes, and you want to look for, see if a certain word appears in them. Hadoop is great for that. It's also great for these types of analytic tasks like the Monte Carlo simulation to calculate pi that we talked about, as well as all sorts of machine learning. So Hadoop is great for both of these applications. Here are some other things that it's good for: grepping through enormous data sets, analyzing your logs, calculating statistics for enormous data sets, running very large simulations, doing extract, transform, load types of things where you want to format data for input to a database, or take it out of a database, put it into another one. Great for machine learning, great obviously for building inverted indexes, for sorting, and much, much more. So what is MapReduce not good for? What it's pretty terrible at is doing things at real low latency. So if you have something that needs to be run immediately, there's a fair amount of overhead that goes in setting up a MapReduce job. So it's really meant for batch processing, although there are frameworks that are trying to address this a little bit more. It's terrible for highly sequential algorithms. If there's no good way to run it in parallel, MapReduce isn't going to help you at all. And then a more practical thing that you sort of think it would be good for, but it's not great for, is joins. So if you're trying to join some set of data with some other set of data, there's no really elegant way of translating that to the MapReduce model. If you're trying to join a large set of data against a small set of data, you can send the small set of data in the distributed cache out to all your nodes, and that works very well. But if you're doing it otherwise, you have to do let's call it a reduced side join, and that uses a little more I/O and everything than you really want it to be. I think that is all that I have. All right. Thanks a lot, everybody, for coming. Really appreciate it. And yeah, please talk to me afterwards.